Hello guys. So today we're gonna start solving frames. This is the first frame that I'm going to solve of a series of examples that I'm gonna post for this class. In the past we have tons of beams examples and drawing shear moment diagram, axial shear moment diagram for beams, but this is the first frame that we're gonna be solving. What is the difference between a frame and a beam? Well, in a beam, the majority of the loads are predominantly transverse loads that produce shear moment. It's not that the axial cannot be present, but the majority of the time is not. Also, when you have a beam, usually you have only one element. In a frame, you have a collection of elements connected, and you can have beams, you can have columns, etc. So then you have to change and switch your local coordinate system, and and because it's going to change depending on if you are in this location or you are at this location here. So this problem is asking you to draw the axial shear moment diagram and also the qualitative deflected shape. This part is referring on how does the structure moves or deform, and we have sufficient information once we complete the moment diagram. Based on the moment diagram and the support conditions, we can have a lot of information that may allow us to do that. The first thing that you have to do is identify the supports, as always. So this is a pin support, this is a roller. You have two reactions here and one reaction there in those directions of the roller. And then the second step will be, is this statically determinate or indeterminate? Because otherwise I don't, at this moment in time, you don't know how to do that, or you haven't studied how to do indeterminate structures. So the first thing is verify that. How do you do that? You just count the number of reactions, you just count the number of members. So this, if you consider this as one full member, because it is, this is a moment transfer connection here, it's not a hinge. If you consider this as one member and you have three reactions, the number of reactions has to be equal. Reactions is 3 and has to be equal to 3 times the number of members, which is 1. So that is a statically determinate structure. So let's start by calculating the reactions. How do you calculate the reactions here? For calculating the reactions, I don't know, you can start by saying summation of forces in x equals 0, and then Cx equals 12. I'm gonna go a little bit faster here because this is not the statics anymore. And now we can do summation of moments at any other point. Could be A, could be C. C, I think, is a little bit simpler from the point of view of working less. At C equals 0. Summation of forces of moments. Look at that. Summation of moments at C equals 0. So we're gonna do moment here, and then what do we have when we moment here? We have AY multiplied by the distance, horizontal distance 30, and this is gonna be a rotation. When you move this in this direction, remember, you put your pin here, move in that direction, the rotation is gonna be like that, so this is gonna be negative. And then you have this 25 plus 25 times the distance, which is 15. And then you have this 12. Once again, you put your pin here, you push it in that direction. This is the direction of the rotation. So this is gonna be plus 12 times 10, 12 times 10, and that's it. You only have one force, two force, and the reaction 1, 2, 3 equals 0. So from here, you can solve and calculate your AY reaction. AY reaction calculator is here. AY reaction 25 times 15 plus 120 divided by 30, and that's gonna be 16.5 keep. 16.5 keep positive. Now what do we do? After we have that, then we do summation of forces in y equals 0. So we can do summation of forces in y equals 0. And then by doing summation of forces in y equals 0, you have AY minus 25 plus CY equals 0. AY is this, and that means that Cy is going to be equal to 8.5 kip. Done. After having the reactions, I always recommend my students to verify those values. Be sure that the reactions are correct. Because if the reactions are not correct, then what is going to happen, somebody always texts me or call me when I'm in the middle of doing something. Okay, if you don't verify the reactions, everything is going to be wrong. So you can do a verification, quick verification. And how do I do a quick verification? I don't know. You just go here and do, let me do summation of moments about any other point, and put all the values of the reactions that you calculated, and that has to be 0. For this particular case, you can do moment anywhere. Now try not to eliminate any force. For example, I can do moment with respect to that point. And what is that point? I don't know. You decide. You say, okay, this is 1 feet. And then you do moment with respect to that point. You put the value here of AY, the two values of the reaction, keep all the forces, and 0 has to be equal to 0 at the end when you do summation of moments. That's it, nothing else. But verify the reactions. This is important step. And a lot of people don't do. I'm gonna do it. I didn't want to do it, but I'm just gonna do it to show you. For example, I'm gonna call that point D, and I'm gonna say this distance here is 1 feet. Arbitrarily. Why don't do it here? Because then Cy is passing through the point, and if I have an error in Cy, I'm not gonna be able to detect that. That's why I'm trying to select a point without eliminating anything. So I'm gonna do summation of moments here. Summation of moments at D equals 0. Remember, this call is for verification. And that's it, verification of the reaction, that's it. Summation of moments at D equals 0. So then you have AY, negative AY times 1, negative AY times 1, plus 25 times 14. I'm sorry, minus. Yeah, minus 25 times 14, minus. Now you have this one, which is also minus 12 times this height, which is 10. Now you have plus Cy, Cx, plus Cx times 20, and plus Cy times 30. 29. You see, that's why I like to put my finger over there all the time. So Cy times 50 minus 1, 29. 29. So let me check again. AY times 1, yes. 25 times 14, yes. Negative, yes. Negative 12 times 10, correct. Plus Cx times 20, correct. Plus Cy times the distance from here to here is 30 minus 1, 29, and that has to be equal to 0. And now you put 16.5 here, you put Cx here, and you put Cy here, and then you get 0 equals 0. Now you are sure that your reactions are correct, and then you can continue. Now be careful, because I have seen students that they have the reactions correct from the first time, and then they mess up, like I was messing up here, for example, in the one of the distances, and then you think the reactions are incorrect, and it happens that your verification is incorrect, not the reaction. So anyway, this is correct. Now we have to start and doing what is called a member and forces. So we have to determine the member and forces in order for us to draw a good shear moment diagram. Now, how do we do the member and forces? We take that beam over there, and we put everything that is in there. So I'm going to put the reaction here, 16.5. That's the reaction for that. I'm going to put this 25. Keep here. I'm going to put the distances, 15 and 15. And at this end, I like to work in this way. Let me explain this to you. I like to have a global coordinate system when I say this. So for me, this is X and this is Y. But as I'm moving element by element, then I have a local coordinate system. And you can call it X1, Y1, X2, Y2, etc. But what I do is this. I'm using this, so my local coordinate system is going to be here, X1, Y1, which in this case is the same as the global coordinate system. But when I'm going to go to this one, I'm going to do this. And I'm going to say, oh, look at that. This is X2 and Y2, and that's going to be my local coordinate system, which is rotated with respect to the global coordinate system. The reason for that, because when you're drawing shear and moment and even axial, you're gonna need that. Depending on that coordinate system, your diagrams are gonna be plotted. So this is very important, even though I'm not doing it right now for everything else. So I'm gonna do this, and at this end, I'm going to have this reaction at the end of B, and I'm going to have this moment also over there, and I'm going to have this force over there. That's what I have. And you can call it B if you want, just because I'm before touching the point B. But then we can calculate these values. How do we calculate these values? In the same way that we calculate by using static equations of equilibrium. Summation of forces in X equals 0. That means that Bx equals 0. Summation of forces in Y equals 0. Then you have 16.5 minus 25 plus By equals 0, meaning By equals 8.5. Keep. By the way, this, start looking at these type of details. This makes completely sense. Why? Because look at this column here. This reaction is 8.5 and it's transmitted directly to that point. So that should be 8.5. If you get here a different value than this one, then you have to go back and verify. Intuition is telling you that. Common sense is telling you that. Learn how to use that part, please. So now, summation of moments, where I like to do moments there, is just my preference. So summation of moments at B equals 0. I'm gonna do that. And then you have negative 16.5 times 30 plus 25 times 15 plus MB, that's it, equals 0. And then you can calculate that moment. And that moment is going to be equal to 120 keep fit in that direction. Perfect. We already have those. Now, the idea is that we move to the next member, which is this column. When we go to that member, that column is here. These forces, these end forces are transferred to this point here. So if the moment was acting in this direction, now the moment is going to be acting in this direction. Action reaction. And this is 120. If this force Bx was acting in this direction, but it happens that there's not any other force, that will be transferred here. And if this By is acting in that way, that means that here you're gonna have By acting in this direction, which is 8.5. Now, we can be a little bit more thorough when we do that. But for this case, it's not necessary, but I want you to start getting familiar and getting familiarized yourself with this thing. So the transmission of the load is not member to member. That doesn't happen like that. It's member to joint and joint to member. So here you have a joint in this part. And that joint, if you draw it, it's going to look something like this. Exaggerating, right? And that joint can be, I don't know, the two members bolted together, welded together. You can have plates connecting them. If it's reinforced concrete, you're gonna have the rebars coming and entering into the other member with the development length or splicing and everything else that you need over there. And by the way, there is a whole design that you have to complete for that joint. You just don't learn it here in this class, but you have to design the joint also. One of the most important parts of the structure are the connections, are the joints. So if you have that at the joint, these forces are transmitted here to this joint. And here is in this way, is transmitted like that to the joint. Now, in the other side of the joint, for equilibrium, if this was acting like that, it would be acting like here. If this was acting like that, I know this is 0, okay? Don't start yelling at me. And the moment is going to be acting like that. And then these forces are transmitted here in the opposite direction. This force down, this force clockwise. And that's the way you do it. You don't need to do that, except you have forces or moments concentrated at that joint. Then it's highly advisable. If you don't have forces or moments concentrated at that joint, you just can jump from here to there. But just keep in mind that the transition is this to that. That's the way it's supposed to transmit the forces. Now let's complete this. I already put the forces here. I'm not putting the horizontal force here because it doesn't exist. Now I'm gonna put this 12 here, 12 keep, the distances, 10 and 10, and here you have one reaction, which is CY, and that's it. You know everything, you know every single value. Now you can verify again your calculations. How do you verify your calculation? Well, if you do summation of forces in X, there's some forces in X. I'm sorry, what am I doing here? Summation of forces. I'm saying this is 0. Why this is 0? Cx is 12. And you didn't correct me. Come on, guys. Do your job. Only have one job. One job. Correcting me. This is Cx, 12. Cy equals 8.5. Okay, summation of forces in X equals 0. So you have 12 minus 12, 0. Good. Summation of forces in Y equals 0. 8.5 minus 8.5, 0. Good. Summation of moments. Where? I don't know. Here. Summation of moments here. Positive 12 times 10 minus 120, 0. Good. Perfect. Now, once you have the enforced members, now we are going to start doing the diagrams, and I'm going to use these enforced members to draw the diagrams in the next page. There are plenty of ways that you can do that. I like to try to keep my diagrams according to the structure. So this is going to be the first diagram for the member AB. And remember what you do here, right? If this is the member AB, you put the reactions, you put everything that you have here, you put the moment that you have here, 120. This value, once again, it was 8.5. This value here was 16.5, and this was 25. And then you draw the vertical lines in the same way that you did before, and then you're gonna have one for axial, one for shear, and one for moment. That's what you do there. Axial, and let's do the axial in, everything is in keeps, right? So keep, shear in keep, and moment in keep per foot. Distances, distances, distances. I like how straight this distance is. 15, 15. And my coordinate system, local coordinate system, is this one. So I start with the axial. Do you have any axial here? And remember, this is the baseline. This defines the 0. And remember, you have to draw vertical lines also at the beginning and the end. Wherever you have a concentrated force, you define your points of interest, your regions of interest, and you do that. Then if you look at the the enforced member, which is this one. I just reproduce it there, right? So basically, axial. Do you have any axial here? No. Oh, this is the easiest ever diagram. No axial. This is your axial diagram. 0. That's it. Now, shear. Okay, this is when this comes into play. If I go in the direction of the load, according to my global coordinate system, then I'm gonna go up, and this is gonna be positive. Same as with the beams. No load here, meaning this is gonna be constant up to that point. This is gonna be 16.5. I go to this point, I find this pushing it down to 8.5. Constant again because there's not any load up to here. Constant here, go to this point, negative 8.5, positive 8.5. I find this point here, force of 8.5 pushing it up, reaches 0, and you do yes. This is good. It closes in 0, so that part is correct. Now we go to the moment diagram. Do you have any concentrated moment here? No way, Jose. This is a roller. If it's a roller, there's no moment unless you have in the beam or in the frame a concentrated moment, which you don't. So it starts from 0. And then you have this beautiful area here, which is 16.5 times 15. This is constant. This is going to be a straight line. So this value here is going to be 16.5 times 15, which is 247.5. There you go, 247.5. And now you find this negative area here, and this negative area here is 8.5 times 15 negative 127.5. So this is gonna come the 247.5 that I had before. 247.5. I'm going to subtract this area because this area is negative, and I'm gonna reach out here to 120. Now I'm gonna put it somewhere here. 247.5 minus this area, which is 8.5 times 15, just for you to review it when you need to review it. And then you reach 120. This is constant up to that point. And now you look at this moment. The way the concentrated moments are, this moment, which in our system we consider it positive for external, when you are studying internal, is the opposite. So it's pushing it down, and now that moment is going to close it here to 0. And then you can say a bigger yes, because this is good. The first one, shear, axial closing 0, shear closing 0, and moment closing 0. Good. Now we go to the other element. And this is one of the difference with beams. Now we do this. It's basically like doing 2 times the work. And the most important part is a global coordinate, local coordinate system, and joint, enforced member transmission. Now we go here, and because this is like that, I'm going to put the other one in this direction. Like that. Now, if you are like me, and I hope you're not, but if you are like me, then I do that. You see, I keep my beam over there, my column over there, but I do that. Now, at this point here, at this point, which is the point B, you put the forces that you found, your end forces. What are your end forces? These are your end forces here, right there. You're gonna put those forces over there. So you're gonna put this one, which is 120. You're gonna put this one here, which is 8.5. There is not any other force here in the local vertical direction. Now you have this 12 keep, and then you have this force CX of 12, and then you have this force CY of 8.5. And once you have that, your coordinate system that we are using. I haven't changed it to green. I like green, but x2y2 is gonna be like that. This is important because if I decided to do it from the other end, then my diagrams are gonna flip, and I don't know if it's gonna be positive or negative for sure. Well, I do know, but maybe you get confused. Beginning, end, concentrated, axial, shear, moment. So when you do the axial, you start from here. And then you find this force, which is concentrated. This force is applying a compressive force here, and it's constant up to the other end. And when you see this other part, it's pushing it down to the other direction. All of this is going to be in compression. There you go, your first axial diagram, basically. Good job. Now, for the shear. I don't have any force here, so I'm starting from 0. Everything here is constant. There is no shear force, so this is going to start 0, 0, 0, 0, 0, 0, up to that point. In that point, we have this force pushing it down to 12. 12. And then there's nothing else here. And this is negative, by the way. And then we find this force of 12 here, pushing it up and taking it to 0. And then we can say again, yes, we're going really good. And now we switch to moment. Do you have any concentrated moment at this point? Of course I have a concentrated moment. Now look at this moment, you see? That moment is pushing up. When I say pushing up is this. I always tell you, easier to remember. You can say clockwise, counterclockwise, whatever, you can say it like that. But when you have a concentrated moment at a point and you're doing the moment diagram, I complete the circle and I look at the direction of this arrow in the left side. If this is pointing up, my diagram, my moment diagram is going to jump up. And that's what I do. At that point, you see the left side of the moment is pushing it up, so this is going to jump up to 120. Now that moment, the shear here is 0, so there's nothing that is going to change that moment up to that point, so that means it's going to be constant. And then we find this negative area. This is positive 120, and then you have negative area of 12 times 10. Those were the dimensions over there. 10, 12 times 10, negative 20, positive 120, constant, constant, and then you reach 0. Now, please, by all means, say yes. And if you want to highlight it, this is a highlight in your life. Definitely mine. Now, that means that your diagrams with the forces, if all of them close in 0, that means that your problem is correct. Now, we haven't finished yet. This is just the diagrams. But if you go back to the original question, we also have to draw the qualitative deflected shape of this thing. Now, the qualitative deflected shape, I don't know if you have done it before, but it depends on the moment diagram, and we have discussed this before, and it depends also on the boundary conditions, meaning the supports of the structure. I'm gonna copy this structure again. I don't know, this desk, my desk, looks like a black hole. It swallows everything, disappears. I couldn't find my black marker, but I already found it. Okay. This is what you have, and this is what you have. Now, this is the pin, and this is a roller here. Of course, you have the force and you have the force, but the force and the force is not the most important thing for me. The most important thing for me is the moment diagram. So for this part, this diagram is positive and positive. This is positive, meaning for this part, my moment diagram is going to be something like that, and this is going to be positive. And for this other part, my moment diagram, which I didn't put it here, and by the way, you didn't tell me anything, this is also positive, so I'm going to put that positive over there, and this diagram is going to be something like this. Something like that. Okay, and this is positive also. Why positive? Why negative? Because if you remember, a positive moment is gonna produce this type of deflected shape, compression on the top and tension on the bottom. Negative moment is gonna produce this type of deflected shape. Happy face positive, frowny face negative. This is gonna be tension on the top, compression on the bottom. And this is gonna be similar to the curvature of that element also. The other thing that you have to take into account is if you're working with a pin, what happened with the pin? If you have a pin, can this move in any direction? No, so do not or don't. No displacement, let me put it like that, no displacement. However, if this is a pin here, it can rotate. If you keep the pin there, this is gonna be able to rotate there. So, rotation. No displacement, but yes rotation. That's what you have in the pin. The roller displays in one direction and rotate also. Both. Let me put this like this. Now, what happened with the fixed support? Fixed support, this point do not rotate, and that point doesn't also deflect. So displacement, no. Rotation, no. And this is extremely important. Now, if this is a moment, also moment transfer connection, moment transfer connection, then if this is 90 degrees, your deflected shape is gonna try to keep those 90 degrees. If this was, I don't know why, but if this was 60 degrees, then your diagram should keep that in 60 degrees. Based on that, we can start trying to do our deflected shape here. Now, what happens when this is pushed in this direction? This point can rotate, right? Can displace. So this point is going to displace, not the roller itself, but the element, the beam is going to displace. Or even the beam with the roller can displace. I don't know, depending where it's attached, the roller. So this can displace to that point. Now what happened with this point? This point can only rotate, but no displacement. But there is a rotation, so that means that here you're gonna have a rotation in that point. And on top of that, this is a positive moment. What does that mean is that the shape, if you look at it like that, the shape is gonna be like that, happy face. So then you're gonna have this part, which is gonna look like that, like that. Now what happened with this other part here? If you use this other part here, this is also positive, meaning it's gonna be a happy face like that. Because this is a moment transfer connection, if this was 90 degrees, this is gonna try to be 90 degrees also here, 90 degrees. And this is gonna deflect, this is gonna rotate, so that means that you can have a translation and a rotation, and it's gonna be a happy face like that. So this is gonna be kind of, if this was a point A, B, and C, the point A is gonna move to a point A prime, and the point B is gonna move to another point B prime. And this is kind of the way the deflected shape is gonna be looking like. Of course, you can do this now with software or by hand, calculate the actual values of the deflection and corroborate with that. But sometimes you are just interested in knowing how this is going to deform, and this is a very good way of knowing that. See you later, guys. I'm gonna record another video with frames for you. Have a good day.